Hi everyone, Assalamu alaikum. My name is Syed Ahmed Shah. Today I'm giving presentation on transistor-based carbon nanotube at room temperature. The outline of the presentation is first I will talk about paper, then paper contributions with some examples, then I will talk about some limitations with these techniques and state-of-the-art approaches I will discuss, and then we will conclude our presentation. So first I talk about the paper. So this paper is published in Nature in 1998 by Cheese-Decker Group. This paper is being cited 8,000 plus times due to tremendous work by Cheese-Decker Group. In 1998, Decker demonstrated how his team created carbon nanotube transistor based on room temperature by depositing single wall CNT and then fabricated by laser ablation of a solution onto oxidized silicon vapors with a gold or platinum electrode that had been pre-printed. So let's talk about transistor. What is this? Why it is so important uh, in electronics? So the transistor is a main electronic component which are using in every circuits for a single signal amplification or also as a switching. So in this article, carbon nanotubes CNTs are needed high gate voltages because they had a low transconductance and high on states resistance and no current saturation. So the fundamental concept behind this research was that instead of using traditional top down silicon electronics, this transistor could be created from the single bottom up single organic molecules such as switching element, and this capture the atomic microscope AFM is used to image a single molecules. So the principle of a carbon nanotube transistor is based on the pre-painting parallel strips on a metal or a silicon oxide substrate techniques were used to fabricate carbon nanotubes, fill effect transistors, which were then deposited in a random pattern on a top. The semiconductor CNTs are suspended between two metal strips. The other source contact is made of metal chips, and while the drain makes contact of the same metal tips in the oxide, the gate oxide is comprised of a silicon substrate. Then for a simple field effect transistor match all the requirements. Uh, so here I'm showing a small video for the formation of a carbon nanotube transistor at the laboratory. So this the creation of transistor was done by the University of Wisconsin who fabricated the transistor at laboratory.
So carbon nanotubes are extremely tiny cylinders made entirely of carbon atoms, and they're exciting materials because they can conduct electricity better than just about any other material that has ever been discovered. However, it's been very difficult to work with carbon nanotubes from a material science processing point of view. So what we've been able to do in our lab is to create transistors made from carbon nanotubes that perform as good as or better than silicon transistors for the very first time. So this has been a dream of the field for the last 20 years, but it's been almost impossible because of these material science challenges.
So there is some challenges with carbon nanotube transistors. Like the first one is the study has some challenges like such as realizing a single molecule device, which have due to difficulties in achieving electrical interactions with individual molecules. And moreover, the second disadvantage of carbon nanotube field effect transistors is that there are only a few materials that can be used as a gate at dielectric, which is either hair or vacuum. Furthermore, by applying gate bias, voltages cause the nanotube to get closer to the gate, limiting how far is the nanotube can be get it. Here, I'm talking about state-of-the-art approaches. So there are some state-of-the-art techniques for the carbon nanotube transistor, like the carbon nanotube transistor are made of warping CNTs in a gate dielectric and then using the atomic layer deposition on to make gate contact according to the state-of-the-art scientific research. Here I'm showing very tremendous video by the development of a transistors with time-wise improvement with their different techniques, including the advantages by the Samsung Foundry. Let's start the video.
Whenever semiconductor technology faced challenges, there has been a guiding light to help navigate the maze. Evolution of transistors is a major component of technology development. Planar transistors have been used for generations with voltage scaling to save power. However, short channel effect ultimately limited usability. FinFETs were the solution and made further voltage scaling possible. Unfortunately, limitations are faced again. For ideal electrostatics, the channel needs to be fully surrounded by the gate. This is known as gate-all-around. Typical GAAs are nanowires. However, integration complexities of nanowires outweigh the benefits. This led Samsung Foundry to create a unique version of GAA with all the advantages but minimal complications. Samsung Foundry.
So in this video, they are showing that with time-wise, the transistor is improved. So they are trying to make this transistor size smaller and more efficient. So in advanced system, there is using a billion of transistors. So in this work, the main approach that to make a transistor really small and tiny with a great efficiency and low voltage. So there are some different transistors they are showing with their advantages, like the voltage uh, graphs between them.
Proudly introduces our multi-bridge channel FETs. MBC FETs consist of multi-stacked nanosheets. One advantage of MBC FETs is that additional area is not required to improve speed. FinFETs need fins to be laterally added, while nanosheets can be vertically stacked. MBC FETs are compatible with FinFET designs. Designers can replace FinFETs with MBC FETs without changing the footprint. Performance can also be improved without area increase.
So there is the most promising carbon nanostructure materials for discovering nanoelectronics, and they have a wide range of applications. Here I am discussing the two examples. The first one is carbon nanotube based transistor to build static memory cells. Or the second one is that single volt carbon nanotube biosensor for detecting a variety of biological micromolecules. So the largest wild animals in the macroscopic size bacteria, and there are tiny microscopic worker laboratory making them non-stop making living things. These workers are proteins are eye special mass grapes which locally serves DNA, which have really important information of mass of protein and other cells. And some other cells have really horror having viruses of bacteria. So because of their small size being a billion times smaller than our eyes observing instead of single protein was difficult in fast. So no, there is a tremendous development in the technology through nanotechnology, especially in biological, through different biosensor, single well carbon nanotube transistor to explore the dynamic and functionalized enzymes and the single molecule like DNA, polymers, protein kinase. By investigating the transaction mechanism, we can establish general design rule and enhance the signal of a protein under observations. And the second example is the carbon nanotube based transistor built to transist these static memory circuits are made from a different or number of transistors to make a random access memory. These design trade up to power and area for typical memories and microprocessor in computers. So uh, I'm now I'm concluding my um, presentation that carbon nanotubes are considered as the most promising nanostructure material in realizing the nanoelectronics transistor. So to understanding the carbon nanotube transistor is enabling and the performance of the transistor is improving very rapidly. Uh, carbon nanotube device present in the bright future to promise the sustained transistor scaling and Moore's law, their practical and manufacturing problems be outcomes. Thank you so much for listening my presentations. Allah Hafiz.